simulating galaxies during the reionization epoch.
Hi, my name is Xiangcheng Ma. I'm a grad student in Caltech working with Phil Hopkins and the FIRE team to use cosmological simulations and galaxy formation. Today I'm going to talk about a topic I'm doing recently of simulating galaxy at the epoch of reionization using FIRE tool. We all know this is the reionization history of the universe. Since the first stars formed at GF30, by the end of reionization finish at redshift 5, the universe becomes from fully neutral to fully ionized. The next generation of observational facilities like the TMT and JWST coming out next year, one key scientific goal is to study the galaxies at these redshifts in much detail, like using the red frame optical to IR and very high spatial resolutions, and also take spectroscopy of these galaxies. The current progress in the theory side for the cosmological simulations, one category is the large volume cosmological simulations, like the work done by Nick Madden, Christian Finnegar, and Illustrated Eagle group. A very large cosmological box, but very poor resolution. The baronic resolution is usually 10 to 5, 10 to 6 solar mass per particle. You cannot really resolve any of the galaxy properties in detail. The other category in the field is people do first star and first galaxy simulations with very detailed pre-model chemistry network. These simulations are very expensive, and they can only do in very small volumes, but also they only probe the first galaxies and first stars at very high redshift. These galaxies are not usually observable even for the next generation of observational facilities. What we do is cosmological zoom-in simulations, just for a non-simulator in the audience. This is simulating dark matter only box from redshift starting 99 to redshift 5 first, and pick a halo here, and do zoom-ins on 3 or 4 Vira radii, and trace all the particles back to redshift 99, and identify a Lagrange volume that this galaxy and for this halo spans. And doing this region, put all the computational power in this region with very high resolution plus detailed baronic physics. And then what we got by redshift 5 is the green is the gas, and the purple here is the stars. So we have a main galaxy here and several other smaller halos and smaller galaxies around in the zoom-in regions. The project I proposed was the HiZ-FIRE project, which is, like I said, it's cosmological zoom-in simulations of galaxies at Z about 5. We take advantage of the detailed baronic feedback physics in FIRE 2, including the cooling, star formation, and all the feedback recipes. The first scientific results are, I just published this paper last month, a couple months ago, with initial 15 zoom-in regions. And these halos, we use very high mass resolution from 100 to 7,000 solar masses for baronic particles. And we probe halo mass in 10 to the 8 to 10 to 12 solar masses by redshift 5. So we avoid the atomic cooling limit by putting the lower mass out here. The first thing we'll look at from these simulations is the stellar mass halo mass relation. So this is a comparison of the relation at redshift 6 and redshift 10. And the sign dashed line here are the best fit 1 sigma region from our simulation suite. The punchline here is the stellar mass halo mass relation does not evolve from redshift 5 to redshift 12. So you can use the stellar mass halo mass relation to calculate the stellar mass function at this redshift. The first technique we use is just count the number of galaxies in a simulated catalog. Although we do zoom simulations, but we can assign each simulated halo an effective volume to convert simulated catalog to a real universe number density. So we can do that. This is what we got for the stellar mass function. The second technique, alternatively, we can use the best fit 1 sigma region of the stellar mass halo mass relation and convolve that with a halo mass function at its redshift to calculate the stellar mass function, assuming each halo hosts 1 central galaxy. So this is what we got the dashed lines here. It agrees pretty well for the massive N and very high redshift. This is redshift from 6 to 12. The only thing that differs is here. At redshift 6, the stellar mass function has a little bit turnover. When you count the simulated catalog, this is probably due to reionization plunging. So these low mass halos are not very efficient in forming stars once the reionization is close to complete. And we also see the faint N stellar mass function goes deeper from redshift to from redshift 6 to redshift 12. This is basically because the halo mass function. So we can also look at the mass to light ratio in these galaxies and do the same analysis to calculate the luminosity functions from our simulated sample. This is the comparison with all the observations so far in the literature. This is without dust, we overestimate the UV luminosity function at the right end. But with dust attenuation model in from our simulations, our results are pretty well. Okay, our results agree with observations very good. So, but one thing I want to mention is by modeling the dust attenuation, we only do very simple analysis for our model from our simulations. We assume 40% dust to matter ratio plus SMC like extinction curve. With very simple like canonical dust models, we can do model the UV luminosity function pretty well with operations. This is our prediction for the cosmic star formation rate density at this redshift. Just take a look at this. There's nothing more about this to say. For a couple of minutes, I want to talk about the claim that a researcher said whether high redshift galaxies are extremely small. This is a plot I stole from Richard's paper that some of the Hubble frontier fields galaxies have very small sizes down to 1 million arc second. We look at this a little bit. We look at this topic a little bit from our simulations. This is an example of, it shows 3 example galaxies. They all have a rest frame UV luminosity function about -16.5. But we show it, and that this is the mass surface density map. This is rest frame UV, rest frame V band images. This one is a very compact galaxy, for sure. But this is the main galaxy, and this is a satellite. But in the rest frame UV, you can only see the satellite, but not the main galaxy. There's a little bit here at the rest frame B band, but still the satellite galaxy dominates. But for this galaxy, this is the stellar mass map. There's a very bright blob here in the rest frame UV that corresponds to a star-forming region that forms 2 by 10 to the 5 solar mass stars at the same time. But this one is not observable in the stellar surface density map, indicating that this is a star-forming clump, but they don't contribute a lot to the stellar mass. So here, this is what it is. So a point here is every observation has a surface brightness limit due to the background noise. So if this is an illustration of that point. So if you're using very deep observation, like the brightness cut is 32 magnitude per square arc second, you can basically see all the galaxies, even the low surface brightness region. But if I drop the UV luminosity surface brightness limit down to like 25.5 magnitude per square arc second, you can only see this blob. This blob is like rest frame UV luminosity minus 13. This is what the point source looks like from our visualization. So this is what you got. So to summarize, the HiZ5 project, it's a suite of high-resolution cosmological zoom simulations, a ratio of about 5. And we find no evolution of the star mass halo mass relation. We can predict a lot of results like star mass functions, luminosity functions at different bands, star formation rate density, stellar mass density, etc. And we also see the dust extinction sets the bright end of the UV luminosity function. For the morphology and size evolution, that is work in progress. We found the right frame UV image is dominated by very small clumps. And if you downgrade your observational surface brightness limit, you only pick up the very bright clumps that you miss the main galaxy at all. And our simulation can have many other applications, like do more detailed analysis on the dust extinction and temperature and predict IR emission. Like we also do rate transfer using these simulations to calculate the Lyman continuum escape fraction, like what I did many years ago. And Lyman alpha nebular lines that has many interests in the near future when JWST is coming out. There are many other applications in this list here. Thank you.
Time for a couple questions. Yes.
Yeah. There are two things we're doing. We have 15 zoom-in simulations, but especially for the low mass end, there are many smaller galaxies around the main halo in the zoom-in region. They have zero contamination from low-resolution particles. So yes, that's a caveat. Sure. We also have what? Okay. We also have zoom-in regions that exactly sit on the low-mass galaxies, but we don't see very different results from even around large halo or isolated dwarf halo. Yeah, definitely.
Maybe one more question, and let's go ahead and bring the next speaker up. Okay, not okay, never mind. All right, let's thank Xiangcheng again.